Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today, inshallah, we continue our class in speed control of DC motors. Last lecture, we stopped with the different types of speed control, which are voltage control, adding resistance control, and field current control of DC motors. Today, inshallah, we will focus on how we can do these controls using power electronic converters, or sometimes referred to as solid-state converters. Simply, if we can see here in the right-hand side, there is a block diagram for DC motor. We have described it in the beginning of lectures using the dynamics of DC machines. So this is a block diagram we described before. This part represents the electrical model of the DC motor, and that part represents the mechanical or dynamic equation of the DC motor. So combining both of them together will present the mathematical model of the DC motor. So we can assume now this is a block for the motor, and we can replace all of this mathematical block by only one block, which is the motor. So this block will be inside of this black box, or this box of motor. And we need to control the machine speed. So as you can see first here for the block diagram of the DC motor, the output is omega, which is the speed, and the input is the voltage. And we have another input also, which is the load torque. Assume we have fixed load torque now, so the input will be voltage, armature voltage, and the output will be the speed of the machine. And we can assume this is for separately excited DC motor, for example. So we have constant field now, and we need to control the speed by means of the applied voltage. So this is a block diagram, theoretical block diagram for the voltage control techniques of the DC motors. Simply, we have the speed of the machine. So we'll have, or we'll measure the machine speed, and using the transducer ratio in order to convert speed to voltage signal. And we will have also the reference speed, which is the required speed, and we will multiply with the same ratio of the transducer, speed transducer, to get the corresponding reference voltage. Comparing the reference voltage with the voltage feedback, or the measured voltage, the result here will be the error of the voltage. So the PID controller now will work in order to reduce this error to zero. So the aim of the PID controller is to reduce this error to zero, which means the voltage feedback due to the actual machine speed will be the same as the reference voltage, which is corresponding to the required speed. And this is the target of the controller. So the output of this part here will be translated to the voltage of the machine. How this part is going to be, or how this part is going to be implemented, this is the idea of using solid state or voltage or power electronic converters. So simply, we will add a power electronic converter here, and based on the output of the PID controller, which will give a control signal to the power electronic converter, and the power electronic converter itself will generate the output voltage. So we simply can add block here in this part. Here يا شباب in this portion. In that part, and this will be the power electronic converter. So the output of the power electronic converter will be the voltage, and the input will be the output of the PID controller, which will be defined in many methods according to the converter used. So this is the idea of controlling the machine speed using voltage control. However, when we try to control the voltage, we may get an out of the PID controller, which may increase the input voltage of the machine. This may lead to increasing current. So it's very important to make current saturation or control the current. So there is another modified control technique, which is considering current control. So simply, we will have the same model of the machine. This is like the previous model, which is here. And we will get the current terminal, and we will use feedback signal to control the current with a reference current. And based on that, here we will have the error, and here we will have the current controller, which is actually a PID controller as well. And this will map the required voltage, which will be used with the converter in order to generate the voltage value, which will be safe in this method because the current here is controlled. So this is another method, but here, as you can see, we inserted here the part of the power electronic converter, which we should add it here in this part. However, in theoretical block diagrams, we don't block the power electronic converters, but this diagram is different a bit. So this one representing the mathematical modeling, including the power electronic converter, but this one only for simulation. This actually this block diagram is captured from MATLAB Simulink, and inside MATLAB Simulink, we just plot the schematic control block diagram like that. So this is the meaning of controlling speed of DC motor. So simply again, we need certain speed, we have to apply certain voltage, but we have to consider current in order to avoid any current increase. So this is the idea of controlling DC motors by means of voltage control technique. The question now, how we can do this? What is the device that will be used to control the converters? We have many devices. We'll start with the first one, which is rectifier. Rectifier device, Shabab, is simply a converter that converts AC voltage to DC voltage, or AC current to DC current. This is the aim of the converter, rectifier converter. Actually, there are many topologies for power electronic converters for each kind of converter. So for rectifier, for example, we have single phase rectifier, which means the AC side will be only single phase, and the output of the rectifier all of time will be DC source. So as we can see, this is the input, and here is the output of the rectifier, and the rectifier here is simply called full bridge rectifier. It consists of 4 switching elements, which are thyristors. This is called thyristor. Thyristor is used with few hundred, maximum few hundred of hertz, around 400 hertz. This is the maximum value of frequency that can be used. But here, for our supply, which is 50 hertz or 60 hertz, the thyristors will be safe because the frequency is in the limit of the data sheet of the thyristors. So here we will have a supply of AC, which can be represented in these sinusoidal waveforms, and the output will be pure DC or variable or whatever. This is what we need to investigate. Actually, the operation of thyristor, we described it before. The condition of operating thyristor, we have 2 conditions. First, we have to apply positive anode to cathode voltage to thyristor. This is condition number 1. Condition number 2, we have to apply a pulse, which is called firing pulse, between the gate terminal, which is this terminal, and the cathode. So for each thyristor, we will apply signal, which is called the firing signal, between the gate terminal and the cathode terminal of the thyristor. So we need 1, 2, 3, 4 circuits just for firing angles. Simply, S1 can be turned on when the anode is positive compared to cathode, and this will happen during the positive half cycle of the AC supply, which means V is positive, and the output here in the beginning will be nothing because there is no current moving in the beginning. So S1 will be turned on during the positive half cycle. However, when we can turn on this thyristor based on the instant of applying the firing angle. Here, for example, this instant, which is called alpha, this is the instant at which we apply the pulse to the thyristor. So at this instant, thyristor 1 or thyristor S1 will be turned on. Simply, when thyristor 1 is turned on here, a current will flow. As you can see, here is a current due to S1. However, we need closed path to flow the current from the supply to the load. So we have to turn on S1 and S2 together. So as you can see in the circuit here, we will turn on S1 and S2 in order to make closed loop for the current. So this is the way to operate the current in the positive half cycle. Simply, so this is the current of switch or thyristor S1 and S2, and it will start at angle alpha and will stay for 180 degrees. So what is the condition of turning off thyristor? The condition of turning off thyristor is nothing but reach to zero current, which is sometimes referred to as latch current. So if the current reduced beyond the value of latch current, the thyristor will be turned off. This can be happened if we apply a reverse voltage with high value. And this simply can be applied here if we could reverse the polarity on S1. As you can see, here the current is still moving through S1 and S2. However, the voltage polarity across S1 is reversed. As you can see, here is the output voltage, and this is the supply voltage. From the instant of pi, which is 180 degrees, the voltage starts to be reversed on the terminals of S1. However, because there is a current inside the thyristor, it will not be turned off. But when we apply a firing pulse at this instant for thyristor S3 and S4, it will make short circuit. S3 and S4 will make short circuit on the switch itself. So as you can see, the positive voltage, which is here now, because the supply voltage is reversed. So the positive polarity here, because S3 is on, will be transferred to this portion. So the voltage across S1 will be reversed. So we could make something called forced commutation. This forced commutation will force S1 to be turned off, and in that case, the current will start flowing in S3 and S4. So if the current starts moving through S3 and S4, it means the polarity of the current in the output will be in the same direction. So as you can see, this is the output current. This is due to S1 and S2. However, from this instant, it's due to S3 and S4. So this is the input, sorry, this is the output current of the rectifier. As you can see, it's varying a bit. However, it's still positive, which means it's DC current, not AC current, because we know AC current means the polarity is moving from positive to negative or vice versa. And the output voltage will be in that shape. So this means also the average value of the voltage here will be positive. So we have positive average voltage and positive average current based on a certain firing angle. Here we apply the firing angle at alpha equal 45 degrees. If we would like to draw the input current I, from Kirchhoff current law, we can see that I equal to I, which is moving in thyristor S1, minus I, which is moving in thyristor S4. So simply, this is a part of S1 and S2. So this is S1 and S2. And this will be the part of S3 and S4. In negative sign, it will be in such way. So this is the AC side current of the rectifier. So this is the input current, this is the output voltage, and this is the output current of the rectifier. If we should have increased the firing angle to, for example, here 135 degrees, as you can see, the starting point of the output voltage shifted a bit to the right. As you can see, here is alpha at 45 degrees. And we know here this is the 90 degrees. So after 90 degrees, the voltage polarity will start from here, but it will stay longer in the negative side. As you can see here, stayed longer in the negative side because we applied firing angle at late time at 135 degrees. So this means the current polarity, the voltage polarity here, or the average voltage, will be negative, which means we have negative voltage and the current will be in the same direction, positive. The current of the thyristor cannot be reversed. All of time, the current of thyristor moving from anode to cathode. So the output current will be the same, positive. However, the voltage here is negative. If we considered negative voltage multiplied by positive current, this means the power is negative. Power is negative, it means the power is moving from DC side to AC side. So for firing angle equal to 135, the power flow will be reversed from the DC side to AC side. This is very important because we can use it in regenerative braking. As we described before, the energy which is stored in the machine will be returned to the supply. So we can control that by means of firing angle. So this part represents positive power flow, and this part represents negative power flow. So this is the first circuit, which is called single phase rectifier. Simply what we need just to understand the waveforms of the single phase controlled rectifier, and also we have to recognize the relation here. The relation, if we would like to get the average voltage of this rectifier, so simply from this waveform, we can make the integration to get the average. You know, the average is the area under curve. So we can start the waveform from alpha and integrate up till pi plus alpha to the sine wave. So it will give you the average area at this part. So if we get the average area at this part and divide it for one complete cycle, it will give you the average value. One complete cycle means the instant of repeating the signal. So one complete cycle here can be represented from alpha to pi plus alpha, because as you can see, the waveform starts to be repeated from here to here. So this is one complete cycle. So this is the way to get the average value. If we apply this relation, we will find that Vt, which is the output voltage or the average output voltage to the machine, is 2 multiplied by square root of 2 divided by pi, which is 22 divided by 7, multiplied by Vt, which is the peak value of the supply voltage, and multiplied by cosine alpha. So this is now the relation to get the value of Vt. As you can see, it's depend on the cosine alpha. You know, cosine alpha is positive between 0 to 90 degrees. So if alpha is varied from 0 to 90 degrees, we will have control the voltage in positive sign. And if alpha increased more than 90 degrees, it means the polarity of Vt will be negative, and this represents the regenerative braking mode. So for all values of alpha from 0 to 90, the operation here will be in motoring mode. So this is the first converter. The second converter, as you can see, these 4 switches are the same like in single phase one. However, there is a third one here because the supply now is a 3-phase supply. The operation here is complex a bit, but we can deduce it in the same way. Simply, this is the phase voltage VAN and VBN, and the third phase VCN. However, the output volt will appear using the line-to-line voltages. And I don't like to go in more details in this part because I know you don't learn the course of 460. But just for your information, this is the output waveform of the 3-phase rectifier. And if anybody would like to have more details about this part, we can discuss this in private, because it's not important, it's not very important in our course here, but just we have to understand that we have 3-phase controlled rectifier, and the output of the 3-phase controlled rectifier during one complete AC cycle, which is from 0 up till 2 pi at this instant, we will have 6 peaks, if you count with me, 1, 2, 3, 4, 5, 6. So we have 6 peaks, and the firing angle alpha started from the reference of this point. So if we make alpha at this instant for S1, so it means alpha equal 30 degrees. So this point is the reference of the firing angle in this converter. So simply, if we have this separately excited motor here, this is the armature circuit, and this is the field circuit, and we apply 3-phase rectifier, we will have a similar relation. V output average equal to 3 multiplied by square root of 6 multiplied by V phase maximum, which is the big value of phase voltage, divided by multiplied by cosine alpha. So by the same way, Shabab, if alpha is varying from 0 to 90 degrees, it will indicate that the average voltage is positive. And if alpha is varied from 90 degrees to 180 degrees, this will represent negative voltage, which means regenerative braking mode. As you can see, comparing this value, 3 multiplied by root 6, compared to single phase, which was 3 multiplied by, 2 multiplied by root 2, you will find the output of 3-phase is much higher compared to single phase. So we prefer to use 3-phase controlled rectifier when the machine power is higher. So this is the application of using 3-phase controlled rectifier, and we prefer it more than single phase. Another important thing for 3-phase compared to single phase, as you can see here, the voltage ripple is lower than the voltage ripples in DC, in single phase. As you can see here, the voltage is not going to 0. However, in the previous case, as you can see here, this is the out voltage, it's going to 0, and we have negative part, which means the total average will be reduced. So we have higher voltage case for the 3-phase, and also the voltage ripples are small, and this can be smoothed using small capacitor if it is required. But to be honest, for the application of DC drives, we don't need to use filtering, because the machine itself will filter the voltage and current. Another kind of converters is called DC chopper. DC chopper is different a bit compared to the rectifiers, because in DC chopper, the input supply is DC. So when we can use DC chopper, or when we can use rectifier, it's based on the available supply. So if the available supply is AC, we can use controlled rectifier. And if the available supply is DC, we can use DC to DC converter. However, there are some benefits of using DC to DC converters compared to rectifiers. Because for thyristor operation can work only with low frequency, as we described. It's working here with 50 or 60 hertz. However, for switched power electronic converters or power electronic switches, like MOSFETs, like IGBT, like MCT, like any kind of transistors, the switching frequency of the switch itself can be high enough to make the output voltage very smooth. For instance, for DC chopper, we can increase the switching frequency, which means turning on and off this switch, up to 50 kilohertz. However, the maximum frequency in thyristors is 400 hertz only. So this will make very smooth output voltage for the DC motors, which reduce the ripples and reduce also the make the output voltage and current much higher power quality. Right. So how we can operate the DC to DC converter? Simply, we have here the supply voltage, and we have here a switch, and this is a diode, and here we connect the armature winding of the machine. Simply, if we connect the switch S, it will be turned on, and the current will flow in the machine. And if we turn it off S, and there will be stored energy in the machine inductance, the current will continue discharging its internal energy through the diode. So this diode is called freewheeling diode. So simply, when we apply switching from this instant to that instant, we call it as on period, which is T on. During that period, the output voltage will be the same as input voltage. So the output voltage converter here will be the same as input voltage. And the current here, IA, will be the same of input current, which is going to charge the machine inductance. For that, you will find the current is increasing. This is شباب at steady state. In this transient, we start current from 0, and it will increase to 1 instant, and when discharge will decrease again. But at steady state, the values of minimum current and maximum current will be repeated in the same value. So this is the first mode, which is on mode. And during off mode, which means freewheeling diode is going to work, the current will be discharged on the machine resistance. So the inductance have the machine inductance has stored energy, and it will be dissipated in the resistance or equivalent resistance of the machine winding itself by using the freewheeling diode. So the current will be discharged here to return to the same value of the beginning current here, which will be called I minimum. So at steady state, the current is going to be moved between I minimum and I maximum for all of time. We have many modes for operating this kind of converters. We have something called continuous mode. At continuous mode, the current will not reach to 0 all of the operation time. However, we have something called discontinuous mode, and at discontinuous mode, the current will reach to 0. This can be achieved by changing the on and off time. So if we control now on and off time, this is going to control the average voltage applied to the machine. So by means of controlling T on during a certain period, fixed period called T, we can control the average voltage. So simply, we can say that the average voltage here equal to the magnitude of voltage multiplied by the on period divided by the overall period. So simply, we can say VT, which is the output voltage, equal to T on divided by T multiplied by input voltage. T on divided T is called alpha and sometimes referred to as duty cycle with the symbol D, but here it's written alpha to differentiate between D as diode and D as duty cycle. However, it's well known as the duty cycle or duty ratio of the DC to DC chopper. So simply, this is the relation of the output voltage and the input voltage for DC chopper. DC chopper is not that simple circuit only. We have many topologies for DC to DC converters. This topology is called class A DC chopper. We have many other classes. We have class B, C, D, and E. The difference between each class, it will have different circuit, and we differentiate between them according to the polarity of the output voltage and current. So as we can see here, the voltage and the current polarity will be positive all of time, which means this circuit can be used only for motoring modes. However, if we need to make reverse voltage or reverse current, or both voltage and current are in negative, we have to use other circuits. And we are going to describe later, inshallah. We have an example here. The speed of 10 horsepower, 220 volt, 1200 RPM separately excited DC motor is controlled by a single phase full converter. The rated armature current is 40 amps and the armature resistance is 0.25 ohms. The armature inductance is 10 millihenry. The AC supply voltage is 265 volt. The motor constant, which is Ka5, or separately excited, we said before, we can combine between machine constant and the flux together in one factor. So Ka5 equal 0.18 voltage per RPM. Take care about this because sometimes the unit is voltage divided by rad per second. So in order to get the voltage, which is the EMF from the machine constant with flux here, you have to multiply by the machine speed in RPM. So what is required here? Assume that motor current is continuous and ripple free. This is good. For a firing angle alpha equal 30 degrees and rated motor current, determine the first speed of the motor. We need to calculate the motor speed. Number two, or B, we need to calculate motor torque and motor power. And simply, we know the relation for single phase rectifier, the output equal to, or the average output equal to 2 multiplied by square root of 2 multiplied by Vp multiplied by cosine alpha divided by. So simply, we have here the supply voltage, which is 265. Yeah, by the way, Vp is the RMS voltage, not the peak value. Sorry, I said before it's the peak value. No, it's the RMS value. So simply, Vp is the RMS value, which all of time is given in AC quantities. So we can multiply 2 by square root of 2 by Vp, which is 265, divided by and cosine alpha, which is 30 degrees in this case, and we can give the output voltage. So this is the output voltage at 30 degrees, and this is the operating condition here. So the required is to get the speed of the motor. In order to get the speed of the motor, we need to calculate the EMF, and we have the value of K5 to calculate the RPM. So simply, we can use the electric current at rated, because the machine here is working at rated conditions. So EF equal to V terminal minus IARA. طبعا شباب, at steady state, we don't care about the inductance, because the inductance will help only in the dynamics. And here we work with the average model of the DC motor, and no need to use inductance in this case. So simply, EA equal V terminal minus IARA. This is V terminal, which is the obtained value from the relation here of the single phase controlled rectifier. minus IA, which is 40 amps, multiplied by the motor resistance. So this is the EMF of the machine. Simply, in order to get the machine speed, we will divide EA by the value of K phi, which is given 0.18. So this is the value of RPM of the machine, 92 RPM. Second, we need to calculate motor torque, and then we need to calculate motor power. Simply, we know how to calculate the motor torque for separately excited DC motor. You know the relation torque equal K phi multiplied by IA. So we have K phi, which is 0.18 volt divided by rad per second. In order to get the value of torque, which is K phi multiplied by IA, we need to get the K phi in voltage divided by rad per second, not by RPM. So we have to convert the relation now from RPM to rad per second. So we have to multiply here by 60 divided by 2 pi. You know, in order to convert from rad per second to RPM, we multiply by 2 pi divided 60. However, here the value is divided by RPM, not multiplied. So we have to multiply by 60 divided by 2 pi in order to give the machine constant in voltage second per radian. So this will be the value of K phi. And now we can multiply this value by current to get the machine torque. So this is simply the machine torque in this case. Finally, we need to calculate the motor power. We can calculate the motor power using IA square RMS multiplied by RA, which is the machine cover losses, plus EAIA, which is the developed power. And for the DC supply, we assume the current is ripple-free. Current is ripple-free, which means it's constant DC. So for constant DC current, we can assume that RMS value is equal to average value. So this value is the same like 40 amps. So we can calculate now B as I square R, 40 square multiplied by the machine resistance, plus EAIA, which is equal to V terminal IA. So simply we can multiply V terminal by IA to get the input power of the machine. Another example here, the speed of 125 horsepower, 600 volt, 1800 RPM, separately excited DC motor is controlled by a three-phase. This symbol means three-phase. 3-5 means three-phase. Full converter, three-phase full converter, which is the second circuit of the three-phase control network we have described. The converter is operated from three-phase 480 volts. What is the 480, Shabab? 480 here is the line-to-line volt. However, the relation is based on the phase voltage magnitude. So we need to divide by square root of 3 in order to get the value of phase voltage. The frequency of the supply is 60 Hz. The rated armature current of the motor is 165 amps. The motor parameters is given RA equal 0.0874. What is required here? LA is also given 6.5 millihenry. K phi is given, and take care again, it's given as voltage divided by RPM. The converter and AC supply are considered to be ideal. Ideal, it means lossless. So there is no any losses in the AC supply or the converter, which means the input power to the converter will be equal to the output power of the converter. Question number 1, find the no load speed at firing angle alpha equals 0 and at firing angle alpha equals 30. No load speed, we said before, no load speed equal to Vt divided by K phi. So in order to get the no load speed, we can use the terminal voltage. However, we need to calculate terminal voltage at firing angle equals 0 and at firing angle equal 30. Assume that at no load, the armature current is 10% of the rated current and is continuous. So it gives us here a hint that at no load, the no load current is 10%. So we have the option now, because the current is known for no load case, so we can calculate the EMF in this case. However, if it's not stated in the problem, we can neglect the no load current or the voltage drop across the resistance at no load, and we can consider the speed as V terminal divided by K phi. However, because here it's stated the no load current is 10%, and we know the value of full load current, so we can calculate the no load current and substitute in the equation to get the no load speed. So we will use it. So simply, for no load condition, the supply voltage is, this is the phase voltage of AC, so 480 divided by square root of 3. So this is the phase voltage RMS value, 277 volt. And now we can substitute in the equation to get the output voltage of the rectifier based on the value of firing angle. So at firing angle equal, a function of firing angle in the beginning. So V terminal equal to 3 by square root of 6 multiplied by V phase divided by multiplied by cosine alpha. So it will be equal to 648 cosine alpha. Now we can substitute at alpha equals 0. So this is the value of V terminal, where cosine 0 equal 1. So EA equal to V terminal minus IA, which is 0.1 multiplied by the rated current. So it's 16.5 multiplied by the machine resistance. As you can see here, the voltage drop across the resistance is very small. So V terminal compared to EF, very, very small value. So if you neglect the voltage drop across the resistance, it's logic. However, because it's given here, we can calculate to get the accurate value. So we could calculate here EA. Simply, we can use now the relation omega equal to EA divided by KA phi to calculate the machine speed at firing angle equals 0. So at 0 firing angle, we got a machine speed of 1959 RPM. Now, we expect if we increase the firing angle, the cosine angle, for sure it will be lower than cosine 0. So this means the voltage will be decreased. So if the voltage is going to be decreased, we can conclude the speed also is going to be decreased. So we expect at 30 degrees firing angle, we will have lower speed. Let's calculate and see. So V terminal now using firing angle equal 30 degrees equal to 561 volt. And we can substitute again in the relation to get the voltage. And as you can see, the voltage is lower compared to the previous case. And the no load speed, as we discussed, it will be lower compared to the previous one. The second part, find the firing angle to obtain the rated speed of 1800 RPM at rated motor current. So now we need to control the machine at rated current and rated speed, and we would like to calculate the value of firing angle which is required to obtain this speed. This is simply like what we have in closed loop control system. In closed loop control system, we will have reference speed, which is here 1800, and we have limit for current, which is 165 ampere, and based on these values, we have to tune the PI controller in order to find the suitable firing angle to achieve the voltage which will obtain this speed. So simply in calculation, we can do that. Now for full load conditions, the back EMF at 1800 will be 0.33, which is the K phi multiplied by N. Take care, K phi here is given, voltage divided by RPM. So we could get the value of EA directly from the value of K phi here and RPM. So this is the value of voltage. And we know the current. So simply we can calculate V terminal now. So V terminal equal to EA plus IA multiplied by RA, and IA is the rated value current, and we could find the voltage terminal equal to 608.4 volt. So now we can substitute in the relation of the converter to get the value of alpha. So simply we calculate before the value of alpha based on the supply AC voltage. It's 648 cosine alpha. And this is the voltage what we need. So just substitute in this equation and give the firing angle. Can you see here? The firing angle is 20.1. If we compared the previous voltage, we can find that speed before at 0 was 1900, 19 point something, and speed at 30 degrees was 16 something, and here is 18. It's in between 0 and 30 degrees. So this is logic answer, where the firing angle here is between the previous two cases. Third part, compute the speed regulation for the firing angle obtained in part B. So now we get the full load speed, and we know the no load speed as well. It's required to calculate the speed regulation. طبعا you know the speed regulation is equal to speed at full load minus speed at no load divided by speed at full load. So the no load speed for this voltage operation, for this condition, is equal to EMF for full load divided by EMF for no load divided by the K phi to get the no load speed. So simply we have the voltage now at the firing angle 20.1. This is now our voltage. So at no load current 16.5, the EMF will be 6 or 6.96 volt. So this is the EMF, and simply we can now divide this EMF by K phi in RPM to get the value of no load speed at this operating curve. Is it clear, شباب? And for any curve, for any voltage value, we will have different no load speed. And if we would like to plot the characteristic now, this is, for example, the relation between speed and torque at a certain voltage. So for any voltage curve, you will have different no load speed value. So we expect at different firing angles, we will have different no load speeds. So don't mix between the no load speed we have calculated in the beginning and compare to the previous case in part B. In part B, we are now operating at firing angle at rated, at which we have firing angle equal 20.1. And this is one of the curves here. For example, let's say this one. So this at alpha equal to 20 degrees, 0.1. This is our case. So expect this is the no load speed we need in order to calculate the speed regulation. So this is different value compared to previous other cases at alpha equal 30 degrees and at alpha equal 0. So we could calculate now the no load speed, which is 1839 RPM, and simply we can substitute in the speed regulation to get the ratio. As you can see, the ratio here is 2.18. This reflects that this motor is very efficient because there is a small voltage drop across the resistance. طبعا يا شباب, this because the resistance value here is very small. If we would find the speed, the resistance value here, you will find the resistance value here is 0.087. It's very small. This is why, شباب, this is because the machine is high current. This is 106 165 ampere. So we expect to have very small voltage drop, and also we expect small speed regulation. Another example, the speed of separately excited DC motor is controlled by a chopper. Now we have here the converter is a DC chopper. The DC supply voltage is 120 volt. The armature circuit resistance is 0.5 ohm, which reflect that this machine is a low power machine. The armature circuit inductance is 20 millihenry, and the rotor and the motor constant is K phi equal 0.05 volt divided by RPM. The motor drives a constant torque load. So constant torque load means at any speed, if we draw the characteristic of the machine, if we have many characteristics like that at different voltage values, this is speed and this is torque. The load torque is constant means we have constant value for load. This is torque load. So the torque load will be the same at any point of machine speed. This is the meaning of constant load torque. So the motor drives a constant load torque requiring an average armature current of 20 amps. Yes, this is very important. If the torque load is constant, this means because we have separately excited DC motor, which means we have constant flux, so all of time the current will be constant as well, because torque equal to K phi multiplied by IA. So the current for constant load torque and constant flux as well, we will have constant current for all of time. Assume the motor constant current is continuous in the DC chopper, means there is no crossing for the DC current, no zero crossing for the current of the rectifier of the DC chopper. So the required here, first determine the range of speed control. Range of speed control, it means during motoring operation. So what is the range of speed control? Yani we have now a supply for the DC to DC converter, and we can control the machine speed. What is the range of the speed control for this case? And for example, in case of rectifier, we can control the voltage from firing angle 0 up till firing angle 90 degrees in the motoring mode. So at motoring mode, we can get 0 voltage at 90 degrees. This is clear because we have in the relation the voltage multiplied by cosine alpha, and cosine alpha equals 0 at 90 degrees. So the range in control rectifier, control the rectifier شباب, is coming from alpha equals 0 up till alpha equal 90 degrees. So what is the range here? How we can calculate the range of speed control here? Let's see how we can find this range. Now, for our case here, we have a supply of 120 volt. This is the input DC voltage of the chopper, and the minimum speed is 0. This is the minimum speed for any motor, so we can control the speed using many curves up till getting at this point 0 speed. So this will be the case of 0 speed here. So the case of 0 speed, which means EA equals 0. Therefore, from the equation of the DC chopper, V terminal equal to, of the DC machine equation, V terminal equal to IARA. So at 0 speed, we have E equals 0, and at that instant, V terminal will equal to IARA. And we have IA equal 20 amps. It's fixed because we have constant load torque. So IARA equal 10 volts. This means we need the output supply, the output of the DC chopper to be 10 volt. So what will be the duty cycle or alpha in this case? Simply, we need to divide the 10 volt by the input volt, which is 120, and get the value of alpha. So we know the relation V out equal to alpha V input. So this is V out equal to V input multiplied by alpha. So alpha to get zero speed equal to 1 divided 12. This is the ratio for minimum speed. Type. On the other hand, the maximum speed, what will be the maximum speed, ya shabab? Maximum speed that we can obtain here at the maximum voltage. We can obtain voltage output equal to voltage input if we applied alpha or duty cycle as unity. This is the maximum possible duty cycle because we can make T on equal to Ts. This is the operation of the DC chopper. And if you can see the pulses, this was the T on. Sorry. So at this instant, this is the full period T. And at that instant, this is T on. So what will be the maximum value of alpha? Yani if you have a look here, if T on equal T, alpha will be equal to 1. So this is the maximum value of T on, okay? T on to be like T, and in that case, the switch will be turned on all of time, and the duty cycle or alpha equal 1. So this is the maximum voltage we can use. We cannot get output voltage from DC chopper higher than the input voltage. So this is our case here. So the maximum voltage we can obtain is 120 volt like the DC input supply. So EA equal to 120 minus the constant current, which is 20 amps, multiplied by 0.5 ohm. So the maximum EMF we can obtain from this converter is 110 volt. So simply, we can now get the speed using this EMF and K5, which is constant 0.05, to get the maximum possible speed. So based on our calculation, the range of speed control is from 0 to 2200 RPM, which is corresponding to a duty cycle from 1 divided 12 at 0 speed and unity at 2200 RPM. So this was the last part which we missed last weeks. So for now, in this lecture and the previous one, we could understand the DC motor steady state response for DC separately excited motor, for shunt motor, and for series motor as well. Also, we described the characteristics of the different types of DC motors. We focused on the separately excited, shunt, and series one. We have many other connections like compound motors, which is like long shunt and short shunt with cumulative or differential compound. The characteristic is different a bit, but it's very close to the shunt and separately excited one. But for the limited time of the course, we cannot cover all of these types. We need to understand the different converters, and these converters will be the same and can be used with other different types of motors. Also, we cover the speed control of DC motors, and we cover the solid state converters that are used to control the DC machine. Thank you very much. Next lecture, inshallah, we will describe the braking, different types of braking of DC motor. Thank you very much.